Alright everybody, so this should be the first lecture that I'm going to upload to the internet. As you probably know by now, we are now conducting the remainder of all classes online, not in person. So I'm going to upload me going through all the lecture slides and post those to YouTube. So you probably know how that works if you've been able to locate this video by now. Also, if you're here, you've probably been checking your email for updates, but I just really want to emphasize the importance of that as we move forward. I realize that we're at a point where nobody really signed up for the way that things are going right now. It's a very hard time for all of us, not just in terms of academically, but of course with the pandemic that's going on. So I just want to let you know that I'm here for you. I'm going to try to do everything that I can to make sure that this goes as smoothly as it can. So without further ado, I'm going to get into the second half of Chapter 7 slides. Now, it's been a while, so just as a reminder, in the last class period before we had to cancel classes, I went through about the first maybe 1/3 or so of the slides for Chapter 7. And in Chapter 7, we're going over, of course, covalent bonding and electron-dot structures. So what I'm going to do is pick up from where we left off. I know it's been a while, but we're just going to move on from sort of the basics of Lewis dot structures and start going into how we can draw something that's maybe a little bit more complicated than just a bond between two different atoms. So I'll go ahead and pull up the slides for this. Your book and the slides here show a pretty good series of steps for you to use to come up with Lewis dot structures. And kind of like previous sets of rules like assigning oxidation numbers, it's important to do these in the same order that you see listed here. So you want to do step 1 before step 2, before step 3, and so on. And step 1 for drawing any electron dot structure is always going to be to figure out how many valence electrons you have. So remember when we talked about drawing the structures for, say, hydrogen H2 or fluorine F2 or nitrogen or oxygen N2 or O2 respectively, we went over how to do those, and we had to count up not the total number of electrons in each of those atoms, but just the valence electrons, because remember, those are the only ones that are involved in bonding. So what we're going to do is we're going to count up how many valence electrons we have based on all of the atoms in our molecule. And if we have a charge, so if we're dealing with a polyatomic ion instead of a neutral molecule, then we need to add one additional electron for each negative charge, or subtract one electron for each positive charge if it's a cation. The next step is going to be to connect our atoms. Now, for any atom to be part of the molecule or polyatomic ion that we're going to be drawing, it's going to need to be connected to at least one other atom with at least a single bond. So we're going to draw lines to represent bonds between atoms, and initially we're just going to put down single bonds, so single lines. And there are some guidelines here to help you figure out how to arrange these. So hydrogen and halogens usually form only one bond. Hydrogen can only form one bond, it can't form two or more. Likewise for fluorine, one of the halogens, that will only ever form one bond. The other halogens have a tendency to form one bond, but it's not absolute for chlorine, bromine, or iodine. And elements in the second row usually form certain numbers of bonds based on their position in the periodic table, and to a certain extent, if you look at the elements directly beneath any of the elements in the second row, they'll have usually the same number of bonds and lone pairs as the elements above them, although with row 3 and below, there are some exceptions to that. It's more absolute for the elements in the second row. So if we look at our second row nonmetals, including semimetals, so we're ignoring lithium and beryllium, starting with boron, You can see the number of valence electrons for the elements in each of these columns in row 2 go 3 for boron, 4 for carbon, 5 for nitrogen, 6 for oxygen, 7 for fluorine, and 8 for neon. Now, if we start from boron, which has 3 valence electrons, the number of valence electrons is equal to the typical number of bonds that forms. So for instance, if we look at a compound between hydrogen and any of these elements, what you'll find is that for boron, the basic molecule for that is going to be BH3, which contains 3 boron-hydrogen single bonds. If we look at carbon, which has 4 valence electrons, it'll form, generally speaking, 4 bonds. So the prototypical example of carbon and hydrogen would be methane, CH4, which has 4 carbon-hydrogen single bonds. Now, starting with nitrogen, as the number of valence electrons increases, the number of bonds is actually going to go down. So for instance, nitrogen has 5 valence electrons, but it doesn't form 5 bonds typically. It typically forms 3. So nitrogen and hydrogen together give you ammonia, NH3, which has 3 nitrogen-hydrogen single bonds. With oxygen and hydrogen, of course, we get water. That has 2 OH single bonds. So again, you can see this pattern that occurs after carbon where if we increase the number of valence electrons by 1 from the 5 in nitrogen to the 6 in oxygen, we're actually going to decrease the number of bonds. And finally, if we move on to fluorine, which has 7, we're going to decrease the number of bonds again by 1. So HF, for instance, hydrofluoric acid or hydrogen fluoride, I guess, if it's not dissolved in water, just has 1 hydrogen fluorine single bond. And of course, as we know, neon, like pretty much any noble gas, doesn't form compounds at all, so it's not going to bond to anything else. You can't form a bond between neon and hydrogen. So that recaps sort of what the general trends are there. Keep in mind, for instance, if you go down into row 3, a lot of those same trends will apply. So for instance, silicon, the element directly beneath carbon, will typically also form 4 bonds, since it also has 4 valence electrons. All the elements in the same columns are going to have the same number of valence electrons. Now, elements in the third row and lower often do behave that way, and when they're part of a molecule, elements in the third row and below are almost always going to be at the center of the molecule. And it's also possible for elements in the row 3 and below to form more bonds than is predicted either by the previous chart or by the octet rule. So what I mean by this, if we look at the highlighted portion of the periodic table, you can see we've got those same groups of elements, boron through fluorine, but instead of being in row 2, we're now in row 3 and below. The elements highlighted in blue there do tend, in many cases, to behave the same way as their row 2 equivalents in the same group, because they have the same number of valence electrons. However, they are larger atoms, and so there will be plenty of examples where we'll see they can have actually more bonds than you'd predict based on the octet rule. So that's step 2. I know it's kind of vague. You kind of need to work through lots of examples to get a good feel for how exactly this should work. Now, for step 3, which of course you'll apply after step 2, where you've basically assigned the central atom and attached the other atoms to that central atom, what we're going to do next is assign electrons to the terminal atoms. So the atoms on the outside, we're going to use lone pairs of electrons from the total number of valence electrons we have available to complete their octets. So of course, any element pretty much is going to want to have 8 valence electrons around it. Now, with hydrogen, remember, its electrons are in a 1s orbital, so to complete that orbital you just need 2. So hydrogen's not going to have 8 electrons around it, it's going to have 2, because it wants to be like helium, which is its nearest noble gas equivalent. But all the other noble gases have 8 valence electrons, and so pretty much any other element will want to have a full octet. If we have any electrons left after step 3, we're going to assign those to the central atom, because at that point we really don't have anywhere else to place them. And then step 5 is going to be to essentially analyze that central atom, determine if it has a full octet, and use one or more lone pairs of electrons from neighboring atoms to form a multiple bond, either a double or a triple bond, if we have a situation where we don't have a full octet around our central atom. So what we're going to get into next is to look at several examples step by step. I'll show you the ones on the slides, kind of walk you through those. I'll also post a video going over a couple examples from the book where, just like we did when we were meeting in class, you can look up those problems, you can try to do them on your own, and then after you've made an attempt to do that, I will have a video for you to look through the explanation for that. So let's start with a simple example. However, this one's going to be a little bit less simple than the first Lewis dot structures we looked at, where we just had 2 atoms. So if we want to draw an electron dot structure for water, H2O, we're now moving on to a situation where we have 3 atoms. So remember, step 1, and this is a step that applies to every single molecule you'll ever draw, is to count the number of valence electrons we have. So water, H2O, each molecule has 2 hydrogen atoms and 1 oxygen atom. Each of those hydrogens is going to bring 1 valence electron to the party, and the 1 oxygen will bring 6. So if we multiply our 1 valence electron from each hydrogen by 2, the number of hydrogens, that gives us 2, plus the 6 from the oxygen gives you 8 valence electrons. Now, so that's the number of valence electrons we're going to have to draw from to put our molecule together. Step 2 is to use some single bonds to connect the atoms together. Now, remember, part of this is going to be to figure out which atom belongs in the center of the molecule, essentially. Now, hydrogen is almost always never going to be at the center of a molecule for the simple reason that it can only have basically a single bond and no other lone pairs or attachments to other atoms. So you can't have a hydrogen with, say, 2 atoms attached to it. Therefore, hydrogens are basically always going to be terminal atoms, in other words, not at the center. So since we can't use hydrogen for a central atom, we only have one other choice, which is oxygen. So in step 2, we're going to put that oxygen in the center of our molecule, and by that I mean that's going to be the atom to which our hydrogens, the other atoms, are attached. So you can see we have single bonds between oxygen and hydrogen, and for any molecule at step 2, you only assign single bonds, and we'll come back to multiple bonds at step 5 if it applies. Now, step 3 in this process, after you've attached those hydrogens to your oxygen, is to assign electrons to your terminal atoms, which in our case would be hydrogen, to complete their octets. And remember, hydrogen will only have 2 electrons around it instead of 8, so we're not going to be able to assign any more electrons to our hydrogen for the simple reason that our hydrogen has 2 electrons available to it with the single bond. So remember, each bond contains a bonding pair of electrons, so each of those hydrogens has access to 2 electrons via the bonding pairs between it and the oxygen. So there's no electrons to place down in step 3. And if we account for how many electrons we've placed so far, we started with 8. Each of those single bonds has a pair of electrons, or 2 electrons, and since there's 2 of those bonds, in step 2 we've used up 4 of our 8 electrons, so we have 4 more to place down. Since we couldn't place any of those in step 3, step 4 says we need to take our remaining electrons, of which there are 4, we're going to put those on our central atom. So since we have 4 electrons, the best way to do that is going to be with 2 lone pairs of electrons. And remember, those can be represented with 2 dots for a pair of electrons. So our oxygen will have 2 lone pairs for a total of 4 non-bonding electrons. And if we count up all the electrons after step 4, we've used up exactly 8 of them, so we don't have any more electrons to place. And then step 5 would be to check the octet of our central atom to see if we need to add any more electrons to it via forming double or triple bonds, for instance. And our oxygen has 8 electrons around it already, which is the ideal amount according to the octet rule, so we're not going to form any double or triple bonds. And in the case of water, the hydrogens don't have any lone pairs for us to do that anyway. So we're done after step 4. That structure you see in step 4 there is the final correct structure for water. So let's move on from water to another example. This one will be carbon tetrachloride, CCl4. So for carbon tetrachloride, of course, for any molecule, in step 1 we need to count up how many valence electrons we have. Carbon has 4, chlorine, being a halogen, has 7. All halogens have 7 valence electrons. Since there are 4 chlorines, we need to multiply that 7 by 4, and then add the 4 from our 1 carbon, we get 32 valence electrons to place down in this structure. So the next step is to connect our atoms. Now, there are several guidelines for assigning the central atom. One good guideline is whenever you see carbon, it's pretty much always going to be at the center of a molecule. Carbon has a tendency to form bonds to multiple different atoms, and therefore is pretty much always a good candidate for the central atom. But if you're not sure, one good principle to apply is look at the elements in your molecules. In our case, that would be carbon and chlorine. If in doubt, go with the less electronegative element for the atom in the center. So if you look up the electronegativity values, which is on a previous slide, carbon is less electronegative than chlorine. So we could use those guidelines as well to tell us to put carbon in the center of the molecule and put chlorines as the terminal or outside atoms. So in step 2, we'll put carbon in the middle, meaning we're going to attach each of our 4 chlorines to that at least one time. So we put down single bonds there. We have to have at least one bond between each of our atoms and another atom, otherwise they wouldn't be bonded to the molecule in any way and they wouldn't be part of it. So in step 2, we've used up 4 single bonds. Remember, each of those bonds is a pair of electrons, so that's 8 electrons used up out of the 32. So 32 minus 8 means that after step 2, we have 24 electrons left. Step 3 tells you to look at our outside atoms, so our 4 chlorines, and to use the remaining valence electrons to complete their octets, assuming we have enough electrons to do that anyway. So I just said we have 24 valence electrons left after step 2. So in step 3, it turns out that each of those chlorines, after step 2, only has access to 2 electrons via the single bond it has to the carbon. So each one would like to have 6 more electrons to end up with a total of 8. Remember the octet rule, oct means 8. So if we put 3 lone pairs on each of our chlorines, that'll give us 6 more electrons, plus the 2 in the bond gives us 8. And so we have 8 electrons around each of our chlorines if we were to add 3 lone pairs to each of them. So 3 lone pairs is 6 electrons. If we do that 4 times, 6 times 4 is 24. So that uses up all 24 remaining electrons after step 2. So once we put in all of those lone pairs you see in step 3, we're going to have all the electrons placed in the molecule. So step 4, which only applies if we have electrons remaining after step 3, doesn't really apply. So nothing to do in step 4. Step 5 is to check our central atom, make sure it has an octet of electrons available to it. And if you look at that carbon, it's got 4 single bonds around it. And remember, again, each of those bonds is 2 electrons because it's a bonding pair. 4 times 2 is 8 electrons. So our carbon is perfectly happy with the number of electrons it has. And so there's nothing to do in either step 4 or step 5. So the structure we have there after step 3 is the correct final structure for carbon tetrachloride. All right. So let's move on to an example where we actually have an ion instead of a neutral molecule. So the only difference here for the hydronium ion, H3O+, is that we have to account for the fact that the entire molecule, or since it's got a charge, polyatomic ion, has a charge, so it has a different number of electrons than if we just combine 3 hydrogens and a single oxygen atom together. So we can tell from our formula, H3O+, that this has a positive 1 charge. So it has 1 fewer electron than it would have if we just combined 3 hydrogens and oxygen and didn't add or remove any electrons. So the way we're going to count up the number of electrons is we have 1 from each of our 3 hydrogens. So 1 times 3 is 3. Oxygen has 6 valence electrons, so 3 and 6 is 9. And then we need to subtract 1 electron for our positive 1 charge. So 9 minus 1 is 8. So we have 8 valence electrons in this structure. Step 2 is to combine all of our atoms and figure out what the central atom is. So again, the central atom can't ever really be hydrogen, so it's going to have to be oxygen, just like it was with water. And for each of those 3 hydrogens to be part of the molecule, we're going to need to attach it to our central oxygen. So we have 3 hydrogen-oxygen single bonds, meaning that we used up 3 times 2, since each of those is a bonding pair. We used up 6 electrons, meaning we have 8 minus 6 is 2 electrons left after step 2. We can't do anything in step 3 because hydrogen should only have 2 electrons around it, so we shouldn't add any lone pairs to that. So step 4 says take those 2 remaining valence electrons and apply them to our central atom, oxygen. And so we do that, and you can see oxygen now has a lone pair of electrons around it. There's nothing to do in step 5 because we have 1 lone pair and 3 bonding pairs for 4 pairs, or 8 total electrons around oxygen. So there's no need to form any double or triple bonds. And we couldn't anyway, since our hydrogens don't have any lone pairs to donate to form double or triple bonds. And so step 4, we're basically done. The only thing you need to take into account is that if you have an ion, to draw the formula correctly, you put the whole thing in brackets and then you indicate the charge, basically as a superscript to the right, kind of like you would the same position in a chemical formula. So you use brackets and indicate the charge if it's an ion. So what you see there after step 4 with the brackets and the +1 charge in the upper right corner is the correct structure for the hydronium ion, H3O+. Okay, so in all the previous examples we've looked at so far, I've told you that there was nothing to do in step 5, so let's change that up a little bit. So for this example on the slides, it asks us to draw an electron-dot structure for CH2O. This molecule happens to be formaldehyde, if you've ever heard of that compound before. So, as always, step 1 is to count up how many valence electrons we have. Carbon has 4, hydrogen has 1, there's 2 hydrogens. Oxygen has 6 valence electrons. If you add all those together, you get 12. So we have 12 electrons to draw in this molecule. Now, step 2 is going to be to figure out how to connect our atoms together. Now, hydrogen's never going to be the central atom, so how do we decide between carbon and oxygen? There's a couple of ways. So again, remember, carbon's pretty much always going to be in the center of a molecule if it's part of the molecule at all. So based on that, we can probably assume that carbon should be at the center. Also, carbon is less electronegative than oxygen. That's another good indication that it is a better candidate for the center of the molecule than oxygen is. And finally, if you go back to the chart, which shows you the expected number of bonds for row 2 elements, carbon is usually going to have 4 bonds around it, whereas oxygen typically only has 2. So since carbon generally forms more bonds, that is also a good indication that it will be at the center of the molecule. So all lines of evidence point to the fact that we should have carbon in the middle, and then 2 hydrogens and our 1 oxygen as terminal atoms. So each of those terminal atoms, the 2 hydrogens, the 1 oxygen, need to be bonded to our central carbon atom, and for each of those we need one bonding pair of electrons. So that used up 6 electrons of the 12 we have to put down. So after step 2, step 3 tells us to assign electrons to the terminal atoms, except for hydrogen, to complete their octets. So we don't add any electrons to hydrogen, but we do have our oxygen, which after step 2 only has 2 electrons around it, which is much less than the 8 that it would like to have. So what we're going to do is we put 3 lone pairs around oxygen, for the reason that it needs 6 more electrons to get to a total of 8. So 3 is the correct number of lone pairs to do that. And as it turns out, we had exactly 6 electrons left after step 2. So in step 3, we've accounted for all of the electrons in the molecule. There's no more to put down. So in step 4, there's no electrons to add to the central carbon atom, so we're not going to do anything there. We don't have any electrons left to do that. Now, we get to step 5, and here's where things become a little bit more interesting compared to the previous examples. If you check on our carbon in step 5, it only has 3 bonding pairs around it, and no lone pairs. So 3 times 2, since each of those is a pair, that gives us 6 electrons around carbon, and we should have 8, remember. So how can we fix that? We don't have any more electrons to put down, so we can't give it a lone pair. What we can do is we can take one of those lone pairs from oxygen, and instead of having it belong to oxygen exclusively, we can share it between the oxygen and the carbon. If we do that, the oxygen will still have 8 electrons around it, because it has access to those via bonding, but now the carbon can access those 2 electrons as well. So we're going to take a lone pair and turn it into a bonding pair between carbon and oxygen. And since we already had a bonding pair there, that means we're now going to have 2 bonding pairs, and so a double bond, which we can indicate with a pair of parallel lines. Remember, the number of parallel lines that you see between 2 atoms in a molecule corresponds to how many bonds there are between them. So in step 5, we go from a situation where we have a carbon-oxygen single bond and 3 lone pairs around oxygen to now 2 lone pairs on your oxygen and a double bond between carbon and oxygen. And if we check that, carbon now has 4 bonding pairs of electrons around it, 1 with each of the hydrogens and 2 pairs with the oxygen. And 4 pairs times 2, since there's 2 electrons in a pair, gives us 8 electrons. And so carbon now has a complete octet. So that structure you see at the bottom right of the slide is the correct structure for formaldehyde. Alright. So that's an example with some multiple bonds. Let's look at an example like sulfur hexafluoride. This is an example where we'll see an atom where we go beyond the octet rule in terms of the number of electrons around one of our atoms. So sulfur, in particular, is in row 3, so that means that it is a large enough atom that there will be some situations where it will have more than 8 electrons around it, and sulfur hexafluoride is going to turn out to be one of those examples. So if we kind of go through this, in step 1, the first step is always going to be to count up the valence electrons. Fluorine's a halogen, so each fluorine has 7 valence electrons. There's 6 of them. The formula SF6 tells you that. So we have 6 times 7 is 42 electrons contributed from our fluorine atoms. And then sulfur, being in the same column as oxygen, has 6 valence electrons, so we need to add 6 more to that. So that gives us a pretty large number of valence electrons at 48. So we have 48 electrons to place down in this molecule. Step 2 says we need to pick the central atom and connect our other atoms to that. And fluorine only ever forms 1 bond, so fluorine's not going to be at the center of this molecule. Sulfur will. So we'll put sulfur in the middle of this molecule and attach all 6 of our fluorines to that. Remember, each of those fluorines needs to be bonded to the central atom for it to be part of the molecule at all. And once you've done that, we have 6 sulfur fluorine single bonds for a total of 12 electrons used, meaning we have 36 electrons left after step 2. So we can use those to complete the octets of the fluorine atoms in step 3. We have 6 fluorine atoms, each of which needs 6 more electrons to get to a total of 8. And as it turns out, if we have 6 electrons per atom and 6 atoms, that'll be 36, which is exactly the number of electrons left after step 2. And so in step 3, we have sulfur in the middle, we have fluorines, 6 of them around the sulfur, and each of them has 3 lone pairs of electrons around it. And that accounts for all 48 electrons, so we don't have any more electrons to place after that. So nothing to do in step 4. Step 5 is to check the octet of your central atom, and if sulfur had fewer than 8 electrons around it, what we would need to do is to form some double, maybe some triple bonds. But if you look at your sulfur, it has 6 bonding pairs of electrons around it. Each of those sulfur-fluorine single bonds is a pair of electrons. So sulfur doesn't have 8 electrons around it, it actually has 12 electrons. Now, sulfur being in row 3 is large enough that there will be some situations where it can do that, but we certainly don't need to add more electrons to it. It's already got more than you'd predict based on the octet rule. So after step 3, there's no more changes to be done, and that's your final structure. Okay, so let's look at this next example. This will be another so-called hypervalent molecule, and these are just ones that violate the octet rule by having more than 8 electrons around the central atom. And there's actually a typo in this slide. We'll cover that when we get to it. So this problem asks us to draw an electron-dot structure for ICl3, iodine trichloride. Both iodine and chlorine are halogens, so each of them will have 7 valence electrons per atom. So we have 1 iodine, so 7 from that, and then 3 chlorines. 3 times 7 is 21 for that. So 7 plus 21 is 28 valence electrons. Step 2 asks you to put the molecule together, at least the skeleton of it, essentially. And between iodine and chlorine, iodine is less electronegative than chlorine, so it's a better candidate to go in the central part of the molecule. So we'll take our iodine, we'll attach the 3 chlorines to it with 3 single bonds. Step 3 asks us to complete the octets of those outside atoms, the chlorines, and each of them only has a single bond after step 2, so we're going to use 6 electrons in the form of 3 lone pairs around our chlorine atoms, and that'll bring us to a total of 8 times 3 is 24, so we have 24 electrons used up after step 3. So that means we have 4 electrons left since we started with 28. So we don't have any more room around the outside chlorine atoms to place those electrons, so we're going to be forced to put them around our iodine atom. So if we have 4 electrons left, that means we can put 2 lone pairs around iodine. And you may notice that between step 3 and step 4, this chlorine on the left part of the molecule seems to have lost a few electrons, and that's not supposed to be the case. So all 3 lone pairs that we put on that previously should still be there. So there should be still those 3 pairs of electrons, which are double dots around that chlorine. So there should be 3 lone pairs there. And after step 4, we've correctly used up all of our valence electrons, so there's no more to place. Step 5 is to check on the central atom, which is iodine, make sure it has at least 8 electrons around it. And iodine has 3 single bonds to chlorine, so that's 3 bonding pairs, and then we put 2 lone pairs on it as well. So that's a total of 5 pairs of electrons around iodine, so 10, which is actually more than 8. Iodine's pretty low in the periodic table, so that's not an inconceivable situation for that. But it definitely means that we don't need to form any more bonds to our central iodine atom. And so what we have after step 4, assuming that all 3 of our chlorines still have their lone pairs, is the correct structure for that molecule. Okay, so the next thing we're going to get into is radicals, and radicals, or free radicals, are a type of molecule where we have unpaired electrons in our Lewis dot structure. These are not very common because, of course, the octet rule says all of our atoms should have 8 electrons around them, or I guess 2 if they're hydrogen, but those are all even numbers. So how could we end up in a situation where we have unpaired electrons? Generally speaking, this is going to be when we have when we count up our valence electrons and we have an odd number of electrons. And the rule is basically the same. We're going to go through things and do them in the same way. We're just going to end up in a situation where we have an atom that doesn't have an octet around it, and generally speaking, there will be one less electron than you would predict based on the octet rule. So, for an example of this, we can look at nitrogen dioxide. This is one of the few relatively common free radicals that you might see in a Lewis dot structure. So, nitrogen dioxide, NO2, not to be confused with a nitrite ion, NO2 minus. So this is just a neutral NO2 molecule. If we count up the valence electrons, nitrogen has 5 of them, the oxygen has 6, and there's 2 oxygens, so that gives us 17 electrons. So that's an odd number. If that seems strange, it's because all of the examples we've seen so far had an even number of electrons. So with the 17 electrons around, well, available for our molecule in general, what you would do is you would put your nitrogen in the middle. Nitrogen forms 3 bonds generally, oxygen only 2, and nitrogen's less electronegative than oxygen as well, so it's a better candidate for the central atom. So you put the nitrogen in the middle, we attach the 2 oxygens to it, we complete the octets of the oxygen atoms, and we end up with exactly 1 electron remaining to put on our nitrogen in step 4. So we just put a single dot down instead of a pair of electrons, because after putting down that 1 extra dot on nitrogen, we've used up all 17 of our electrons. And if you count up the number of electrons around nitrogen after that, you end up with 2 single bonds, and a single electron gives you 5 electrons. We're not going to be able to complete the octet for nitrogen, but we can do better than 5, so you can take a lone pair from one of the oxygens and turn it into a second bonding pair between your nitrogen and oxygens, and you end up with the structure that you see here, where we have a nitrogen-oxygen double bond. That oxygen has 2 lone pairs around it, a nitrogen-oxygen single bond, and that oxygen will have 3 lone pairs on it, and just 1 electron around our nitrogen atom. So this is a free radical since we have an unpaired electron around our nitrogen.